Thanks. Well, good afternoon, folks. Thanks for coming to my session. My name's Sangwin, and I'm in the Maths Department at the University of Edinburgh. This is a talk about mathematical induction, which was postponed from the conference last year. So let me share my screen and let's get started. So I'd like to talk a little bit about proof by induction. And since this is a talk at the SMC conference, I'm going to focus on induction in SQA Advanced Highers, which for those international visitors are the exams sat by high school students at the end of their school career in Scotland. I'm going to talk a little bit about what proof by induction is, but I'll keep that short. I'm going to assume that most people have seen induction before. I'm going to talk a little bit about history of proof by induction. I'll talk about some examples which have cropped up in our local exams and comment on those a little bit. I shall also share with you some fun examples, some of my favorite things that are proved by induction, and we'll talk about why I like those particular example proofs. I will then talk about what happens when induction goes wrong and what students struggle with, because I know this is a challenging topic. It persists, the challenges persist. I'm teaching induction as part of our year 1 proofs and problem solving course in semester 2 at the University of Edinburgh, and our undergraduate students struggle with induction as well. So we'll talk about a little bit about that. And I'd like to encourage everyone to post thoughts about what students find challenging about proof by induction on this Padlet site, which I put a link there, and I have posted a link in the chat, so you can go straight to that site. The advantage of posting on something like Padlet is that will survive beyond the Zoom chat. Once the Zoom meeting is over, we will lose the chat. So it'll help us collate things there. And then we can talk about what to do about some of these issues when induction goes wrong, and how we can address that with the teaching. So before I get started in earnest, I just want to acknowledge the contribution of my PhD student, Mariam Alafaj, who is working on online assessment with me, and she and I wrote this paper. The paper has already appeared in the SMC journal, actually, because the talk was due last year. So she and I co-authored the paper that this talk is from. So I'd like to thank her for her contribution to the background and helping me write this up. So one of the things about mathematics is proof. That's the hallmark of mathematics. And I think it's an important part of learning mathematics is learning to write proof. And how do we write proof? We write proof using conventional forms. There are some things that we accept as a legitimate proof, and proof by induction is one of those. And I think proof by induction is one of the few forms of proof that we really teach in an explicit and conscious way. I think other forms of proof often arrive a little bit by way of osmosis. So we could frame some calculus argument as a proof, but we don't. We just frame it as a kind of calculation often, and solving equations we could frame more formally, but we don't. There's actually quite a lot of logical reasoning involved in solving equations, and there are edge cases and special cases and issues with function domains and all sorts of things. That means that what looks like a calculation often has a lot of reasoning in it, and sometimes, and I think for some good reasons, we don't highlight that. So when it comes to what is a mathematical proof, sometimes I think proof by induction is one of the first explicitly taught forms of proof. And the basic idea is very simple. We start from a true statement, and then truth is maintained as we move forward step by step. And the two things, starting from truth and maintaining truth, means that we can conclude that a particular statement is true for all values of n, right? So the goal is to prove that a whole class of statements is true, and we do that in this way. And this is quite different from inductive reasoning or experimental reasoning, or as valuable as those things are, as essential as those things are. Proof by induction is not about that. Proof by induction is quite a formal, logical process. So I'm going to give this example. I think this is the example that everyone starts with when I'm looking. Well, Mariam and I did quite a comprehensive research of all the books on teaching maths. This is the course textbook that we use in Edinburgh for our first year proofs and problem solving course, right? It's got a sort of section on induction on it. And this is the problem that lots of people start with. Prove that the sum of the first n odd integers equals n squared. So let Pn be the statement, and I have reformulated a English sentence into an algebraic statement. So that's my induction statement. The sum of the first odd number 1 is 1 squared. So this first statement is true. And I've written that out fully. Assume that Pn is true. Then we've got this algebra. I've got the sum up to n plus 1 on the left. We do our algebra. We use the hypothesis that Pn is true here, and we conclude that it's n plus 1 squared. Hence, P of n plus 1 is also true. So that's my induction step. And since P of 1 is true and Pn implies Pn plus 1, it follows that Pn is true for all n by the principle of mathematical induction. So these 4 things make up a proof by induction: a clear statement of what we're proving, a base case, typically P of 1, but it doesn't have to be. We prove an induction step, typically P of n implies P of n plus 1, but there are variations on that theme. And then we have a conclusion. So some of the variations are detailed in the paper, and I don't want to talk about that today. So that's the structure of a proof. And steps 2 and 3 are really mini proofs of their own, right? We're proving a particular single statement in 2, and then in 3, the idea is that we have an extra hypothesis that we can use, P of n, and we have this goal, P of n plus 1, and that's the way it works. And then we combine these 2 separate proofs with a conclusion to get our complete proof. And this really is a formalization of pattern spotting. You know, we have a pattern that we spot step by step, and we realize how to get from one case to the next, and we formalize this pattern spotting in a formal proof. And actually, this form of proof is quite late. It really only comes in the mid-1800s. Many mathematicians, Euler, Cayley, and others, preferred examples. So this is from Euler's Elements of Algebra. This fact can be seen more clearly by an example than by an argument. If you look at Cayley, when he proved the Cayley-Hamilton theorem, he proves it for cases 1, 2, and 3, and then just says, you know, it's true for all n. It's amazing. We wouldn't accept that now. I'm just going to switch to my document camera. I hope I'm still sharing my am I still sharing? Yeah, looks like I'm still sharing. This is Euler's Introduction to the Analysis of the Infinite. And if we actually look at what he writes in here, this is Blanton's translation. This is typical of the way Euler writes. He does lots of cases, sine 0z, 1z, 2z, blah, blah, blah. We conclude that nz is this, right? And he just spots a pattern and gives us a pattern. And he does this page after page, right? He just gives patterns and then gives the general case. There's more of it here, right? He just gives patterns and then a general case. And that is his kind of style. That is his style of writing. And I don't think that would pass muster in the 21st century as a legitimate proof by induction, right? We're more formal than that, and for good reasons. But these sorts of arguments are really quite old. One of the things I wanted to do in preparing this talk is actually look at induction and look at the history of it. And the first recorded proof that we can recognize goes back to Gershon, Levi ben Gershon, 1321, and he's actually proving associativity of multiplication. So it's quite a foundational result, but it's an identifiable induction style argument where he says, you know, three things in a product. It doesn't matter which order you multiply them together, and then you can just add them step by step. But Pascal is probably attributed with the first recognizable induction argument. And the first use of the phrase induction is found in De Morgan, so that's 1836. And I've reproduced De Morgan's proof here, so I'm just going to pause and be quiet for 2 minutes and let you read De Morgan's proof. Well, I'm sure I haven't given everybody enough time to read this. I've read it a few times and I still find it really very difficult to read and understand. And I hope you have an opportunity in the discussion to return to this. But just to compare it, it's the same theorem that I chose at the beginning of the talk. And I chose the theorem at the beginning of the talk because De Morgan chose this as the first ever, it happens to be the first ever recognizable modern proof by induction. This is my presentation. Just to remind you of my presentation, I have really made a clear statement. I've got a clear base case. Here's my induction step and my conclusion. And I'm using a lot more algebra, right, than De Morgan does. Anyway, proof by induction for end of school, beginning of university, there's no shortage of problems that can be proved by induction. So if you are an examiner, and I have to write university exams, this is quite a good topic. There's plenty of things you can ask students that are that test whether they understand this subject. Divisibility, summing series, lots of examples of summing series. We've just seen one, including rational expressions and other things proving that the formula for a sum of a geometric progression. Slight wrinkle here that it starts at 0 and not at 1, but that's fine, right? It's just one of the variations on induction. And then formulas for things, nth derivative, trig functions, all sorts of things that you can prove by induction in that way. In the SQA Advanced Highers, the current specification says that aspects of sequences and series are introduced, including summations proved by induction. So it's explicitly on the current syllabus. And I have to say, since 2000, I think the SQA Advanced Highers have contained a comprehensive range of questions and a really interesting variety of questions. And for your convenience, for completeness, Mariam and I in our paper actually collected, this is from the SMC journal, it's already been published, but we collected together all the questions in the last 20 years from the SQA Advanced Highers of what are proved by induction. So the very first one that we've included, 2001, we have got the sum of a series, 258. Then there's a divisibility thing. Then there's another summation formula. This is the nth derivative type question, another summation formula. And now whether these are still on the current specification, right? This current specification talks about sequences and summation formulae. But anyway, here we go. So there's a good variety of things, a good variety of, including, matrix powers, all sorts of stuff that you can prove by induction. And I have to say, I think this is an interesting and comprehensive range of applications by induction, and I hope folks who are teaching SQA Highers find this list that we've pulled out a useful resource. So I'm going to propose that we have a 10-minute workshop now, and I'm going to suggest that we do 3 things. I'm going to set 2 induction problems, which are amongst my favourite. Which if you haven't taught this subject and you'd like to have a go at these, that's great. And if you do teach these subject and haven't seen these examples, please have a go. The first one is prove by induction that an equilateral triangle of side length n can be covered by precisely n squared equilateral triangles of side length 1. Okay. Oh. Prove by induction that for any n, a 2 to the n by 2 to the n square grid with 1 square removed can be covered by L-shaped tiles. Now I'm just going to elaborate a little bit, excuse me. An L-shaped tile is just an L-shaped tile made up of 3 tiles, right? And what do I mean by a 2 to the n by 2 to the n grid with 1 square removed? So here we've got a 2 cubed 8, 2 cubed 8, a 2 cubed by 2 cubed grid, and I've removed 1 square, and the task is to prove by induction that you can cover the rest of the grid with these L-shaped tiles, right? So I've done that in this particular case. There's my tiling. Of course, I could have put this square anywhere else in the 2 to the n by 2 to the n square grid, and I would have to tile the remainder, and then we need to prove by induction on n that that's what we want to do. So just for fun, these are 2 of my favorite induction problems, and I'll explain why after you've had a go. And then the third thing is, what problems do students have with induction? If you've taught induction and you're experienced at teaching induction, please share your comments on Padlet, and then I will try and pull those together in about 5. Well, let's reconvene at 1:45, and that will give us 25 minutes to discuss your comments on induction and these problems, and we'll move on from there. Okay, so I've just posted that link in the chat again, and I will just share my screen and leave you with those problems on the screen. Yeah, okay, folks, thanks. I'm going to interrupt now. We've got a few comments on Padlet. So if you'd like to post some things on Padlet now, that would be really appreciated to seed the next discussion. Donald, you spotted my ruse with the first problem. Well, if people, let's reconvene. If people would like to switch their cameras on, bear in mind we're recording if that's intrusive, but if you'd like to switch your camera on or switch your microphone on and comment on, let's comment on the problems. Anyone got comments about those two problems? Has anyone seen those two problems before? A couple of shaking heads. No?
I think the second problem is quite hard with the word any one square removed. I think that makes it really tricky because I'm not sure how to prove I'm being exhaustive. I can get the result if I pick, a particular one, shall we say, and always pick that one. But I think I don't know if I can extend it. I haven't seen yet how to extend it to any.
It's got this double element of generality, hasn't it? So we've got the generality on the 2 to the n, the size of the square, but there's also some generality on where that missing tile goes.
Yeah, that's
and actually the reason this is my all-time favorite induction problem, because there's almost no algebra in it when you see the answer. I'm not going to go through the problem. I won't ruin it for that. I came across this problem in Daniel Velleman's book, How to Prove It, a book which I used as an undergraduate. It had just been published when I was doing my undergraduate, and it's in his book. And I've since traced the genesis of that problem, and the reference to that is in the SMC paper for where this problem was devised. And I definitely think one of my responsibilities as a teacher is to curate these problems when I find them. Right, there are this problem has got for me a little sparkle about it. There's something a little bit special about this particular induction problem. So yeah, and I've used it a lot with students. It is definitely not the first problem that I would give as the first induction problem, but at a certain point, I think this problem is hugely valuable to reveal the essence of what induction is getting at, right? And I will say no more. It's just lovely. I absolutely love this problem. Paul's got the second one, and an exclamation mark. It definitely deserves an exclamation mark, Paul, for sure. Right, let's have a look at the Padlet comments, shall we? Algebra, yes, algebra. Yeah, I recognize that. Algebraic manipulation, following the algebra. Right, and so I think there's some good reasons why induction in algebra is difficult. So when we first encounter algebra, it's typically solving equations, isn't it? And when we're solving equations, we're making everything smaller or simpler. We also know where we're going, right? We're trying to get x equals at the end, right? Because I sometimes say driving the algebra bus. When we're driving the algebra bus, we know what kind of destination we're going to get to. Now with induction, and especially with summation formulas, we've got a relatively complicated algebraic expression on the right anyway, probably more complicated than many things we do at school. And suddenly you have to put n+1 in it. So, and then get there without making any mistakes in a multiple consecutive lines of derivation, right? It's all stacked up against you. So for sure, the algebraic reasoning is difficult. And the sigma notation, somebody there has talked about the sigma notation. For sure, this sigma notation business. And with the summation formulae ones, taking the last term off and still ending up with some sigma notation, and then recombining it back into a single algebraic expression, that's also very problematic. And I absolutely recognize that with my undergraduate students. And when I'm talking about undergraduate students, I please don't interpret anything I say about my undergraduate students as criticism of what teaching they get at school. There are so many complexities in proof by induction. I think it's completely unreasonable to expect a typical student to get it first time, right? So a lot of the things that are still problems at university are because it's just the second time they've seen it, right? That's all it is. And most of us need to see these kinds of things more than once to avoid all the pitfalls and traps and all the rest of it. So patterns and general formula. Yeah, I've talked a lot with colleagues about using induction as a way of spotting patterns in algebraic expressions. What does it mean to have cn+1 in this, even if you maybe need to do, so what is it? It's sums of the squares, n+1, 2n+1, right? When you put n+1 in there, it's 2n+3, and you suddenly got to recognize that that's the 2n+1 for n+1. Oh, you know, it's just this pattern spotting. Yeah, absolutely. So I recognize a lot of the comments on Padlet. So not everyone's posted on Padlet, but thank you for folks who've done that. I have prepared some slides, which I need to share. Sorry, folks. Where are we? I'm back to sharing now. Okay. So I had prepared some things that I recognize from proof by induction. This paper, kind of interesting paper by Ernest from a long time ago, actually, who looked at proof by induction specifically. And I recommend this paper. And Mariam and I found this very useful in preparing this SMC paper from which I'm giving this talk. This difference between heuristic induction and mathematical induction. Well, you know, Euler got away with heuristic induction and pattern spotting, and for him that was a proof. So why? And I think that's a very valuable form of reasoning. It just doesn't pass muster as a formal proof by induction yet. So somehow we've got to separate out something which is very valuable to see the underlying pattern and understand the maths, and this formal way of justifying it, which is somewhat different. So it's not surprising that students will find that difficult and continue to find that difficult. This business of assuming what you want to prove and then proving it, of course, right? It just looks, well, if P of n is the goal here, then I've just assumed the goal. Well, you've been shouting at me for years that I've got to, you know, that's the conclusion, and suddenly I'm taking what looks like the conclusion and making it the hypothesis. So that's crazy. There's no surprise that that creates all sorts of difficulties for our students, as it, yeah, perfectly reasonably. Complex statements, right? And that's absolutely that. Partly that's the algebra, but I've put here dealing with a statement as an object. So one of the things which my students seem to find very difficult is dealing with the whole statement. P of n is a whole thing, right? And particularly with summation formulae, it is the right-hand side, right? It's the answer to the problem. What's the sum? The statement is not the whole statement, it's the answer to the problem. And that's a really difficult one to dislodge. And so, Donald, when you were talking about the, what is the statement here? The statement is that you can remove the square from anywhere. So that's why at a certain point I find this problem useful, because to understand the statement, you really have to accept what the statement is. And it hasn't got a summation formula in it, right? And so that's what that contributes to one reason why I find this particular problem so helpful in my teaching. And people ignore the base step. Well, mathematicians do this, right? My colleagues write proofs for inductions for students and just say, oh, the base case is trivial, and just dismiss it, right? Well, of course, to an expert it is. Right? And at any reasonable algebraic level, what I just wrote down, that 1 squared is the sum of the first 1 odd numbers. I mean, that's utterly, I mean, what have I done there? Nothing of any substance, right? So why are we surprised that the students ignore the base case? I mean, of course they do. Of course they do. But it's the anchor to the chain, isn't it? It's really essential. And the last one is that it's only a tool to some finite series. Now, of course, there is no end to interesting finite series. And if you look in any textbook that covers induction, at least half the problems will be summing series because they're a rich source. And the other nice thing about that is you can provide a template for a proof by induction with finite series and concentrate on the algebraic bits, right? You don't have to concentrate on the logic or the layout or anything else. You can just deal with the sigma notation and the algebra, and that relieves the cognitive load. So actually, I always start off with lots of finite series, but then I need a good collection of things like the tiling problems to break that as a possible misconception that might result from using a pattern to relieve cognitive load. Right, there's just a lot going on in the design there. So you have to break that at some point. And I like my L-shaped tiles as a good one to help me do that. Although, of course, it persists, as you'd expect. And let's have a look at what SQA examiners said. These are from excerpts from some of the course reports. Mariam and I had a lot of fun looking through these. Candidates found great difficulty in communicating and explaining. Yeah, so that hasn't come up in the... That hasn't come up in the comments, I don't think. But I think probably proof by induction is amongst the first kind of proof where you really are reasoning at school. So students are probably not used to actually communicating what at this stage is a reasonably extended piece of mathematics. So fair enough. Lacked rigor and understanding, process of communication again. Important elements of the logic, a correct statement of the induction hypothesis. Yeah, this is a bugbear of mine, actually. How can you prove something if you haven't stated it clearly? In my example, I deliberately gave it in a rhetorical form and then reformulated it as an algebraic expression. And I think there is value in that double step. So I consciously, again, not perhaps the first time I set induction problems, but there is a point where I deliberately make my students write out a clear statement which is not in the form that it's given to them, right? So that there is this business of dealing with an algebra, right? And 2018, the algebra again, unsurprising. I can't see my title on my slide. What's this? Yes, so this is dealing with the statement as an object, which I've already mentioned. So this was a problem that I just ran this year with my undergraduates. Again, it's some of a series. And I just asked the students to write P of n plus 1. Let Pn be this statement, write P of n plus 1. So in the chat, what percentage of the students, first year undergraduates, what percentage of the students just think that Pn plus 1 is equivalent to that? I hope I got it right. I think I got it right, yeah. So just guess in the chat. We'll have a quick look at the chat. So I have to get my chat window up now. I'm being... chat, there we go. Oh, 70, that's very pessimistic. 32, most, 60, gosh. 80, oh, have we taught them nothing at school? Well, there was, it was 40 basically, right? So, you know, still a decent percentage. They will have seen, most of them have seen induction once. I've certainly tried to hammer this home, and it's something that persists. It's a misconception that persists, and so we just have to acknowledge that. That's the way it is. And there's a problem when one of the problems about induction is that people say, "Oh, it's this mindless incantation. You just say this," and I think that's both a strength and a weakness. Giving students a structure, giving students a formal structure actually relieves you of worrying, is this a proof, right? If you can follow a pattern, it's easy to know that you've done the right thing. And that's both a strength and a weakness. And there is definitely this well-established psychological effect called the expert reversal effect, right? What is useful for a novice, a highly structured, this is the way you're going to write the proof by induction, and you will use this form of words, And no, you won't dismiss the base case as it's trivial. You will spell out the base case details, right? That's useful for novices, but that might actually hinder an expert because it slows them down and they don't need that detail, right? That's just expert reversal effect. So this is both a strength and a weakness. And I definitely both try to be honest with my students, but I try to instill a fairly formal approach to the way that you start to write proofs by induction. Of course, they've already learnt it once. This is the second try for most of them. And that removes the worry of deciding, is this proof correct? Of course, anything formulaic can become mindless. That, I mean, in a sense, that's why we have algebra. You just turn the handle and off you go. And that's great. It relieves you of having to worry about every situation. I mean, do we really want to read and write proofs like De Morgan's? I don't. I mean, that's terrifyingly difficult to understand and probably full of errors if you write like that, right? I mean, this is goes back to Leibniz trying to find a universal calculus by which we could immediately tell if a proposition is true. He tried to find a symbolic language that would remove the worry of whether something is true. People have been looking at this for hundreds of years. So yes, of course it can become routine. And I think that is both a strength and a weakness that we need to acknowledge. So ways to avoid these problems. And I think for me, it's trying to create a rich diet of questions. And I think the SMC past exam questions are a rich diet of problems, right? They don't have some of these pictorial ones in, but then the current spec says summing series and introducing sequences, right? So they're probably not in the spec. And we can do interesting things with even routine problems by just changing them a little bit, either dressing them up as I did with the triangles, cover the grid. That's one way to dress them up. Or we can bring out, of course, we can provide practice on sigma notation. We can separate out. Mariam and I have been developing learning materials where we separate out concerns so that we have some questions that ask students to write Pn+1, and then we ask them to do some algebra, and then, wow, in the next problem, that's just what they needed for the induction problem, but now they have to put those algebraic steps into an induction instead of having to do the whole lot in one go, which is a big ask. And here's another way to structure materials. We've got this statement, and Pn implies Pn+1. So let's go ahead and prove that. And then you have to prove that this statement is never true, right? So this is a kind of crazy thing. How does Pn imply Pn+1? But it's just nonsense, right? So this is all about the heart of what mathematics is. The heart of mathematics is following consequences of assumptions as opposed to absolute truth or figuring out the way the world works, which is what physicists do, right? So this kind of dressing up as part of the diet. Again, this is not the first problem you do, right? This is the polish. But these are some ways that I've tried to avoid these pitfalls with students. I think mathematical induction is a really important and interesting topic, and I think it's a great opportunity at school level for advanced higher students. They need to combine correct algebraic reasoning. Everyone said that in the Padlet comments. It's this manipulation of formal statements, and that's the heart of mathematics, is dealing with a statement as a thing and understanding it and trying to prove it. It's also probably a rare example of a really multi-step process at school level, I'm guessing. I can't think of, you get some maybe partial fractions but anyway. Finding the answer versus proving the statements are true. That's kind of interesting distinction, and maths increasingly at university level moves on to proving statements are true rather than just finding the sum of the series. Actually, I guess that's one thing I haven't said. The downside of proof by induction is you need to know the answer before you start. It doesn't solve the problem, right? So that is, of course, the downside, but there we go. And so for all these reasons, I think induction has a uniquely important place in school maths curriculum, right? For all these reasons, it's an excellent subject, I think. So questions and comments?